Good afternoon, everyone. We thank you, the organization, for the opportunity to present our work. This research is a collaboration between two departments, Department of Architecture and Department of Civil Building and Environmental Engineering of University Federico II di Napoli. The topic addressed is a critical investigation of the use of artificial intelligence algorithms for cultural heritage classifications, based on some still ongoing research questions that have emerged from the studies that our two groups have conducted in recent years. The work that will be described focuses on evaluating the quality of survey data, but we will also try to present further advances in this research.
Okay, today the use of artificial intelligence algorithms for semantic segmentation of cultural heritage data in the form of images or point clouds, mainly at the scale of urban and architectural application, is well established. The advantage of their application is the facilitation of several activities related to the issues of modeling, heritage management, monitoring, and preservation. The state of the art shows that the approach to date focused on the use of AI algorithms, referable mainly to machine and deep learning, in relation to the way relevant feature extraction is performed and the degree of autonomous learning. Although the use of algorithms based on convolutional networks is becoming more widespread, our comparison of them shows that the random forest algorithm is among the most robust. Based on the comparison of several parameters considered significant, for example, the robustness to noise and data size for training, the random forest provides performance comparable to the best deep learning algorithms, with the advantage of requiring less data needing for training. To date, the well-established workflow based on the use of a random forest and made available by FBK's 3DOM unit basically consists of 4 phases, from the input data to the predictive model. Specifically, the supervised algorithm is pre-trained to recognize 10 classes of macro elements, with training on manually labeled data in Cloud Compare related to different architectural typologies. The training carried out in Python is based on the selection of some geometric and radiometric features computed in Cloud Compare. Each of these steps requires a series of critical insights in relation to certain research questions that are still open. In particular, with respect to the input dataset, the questions concern the influence of point cloud density, the dependence on sensor type, and the influence of collected data parameters. Regarding the feature extraction phase, the questions instead concern the possibility of computing other features and the influence of their selection on the results. Finally, in reference to manual annotation of classes for training, questions concern the influence of annotator specialization, degree of agreement, and the influence of architectural typology. Therefore, the objectives of our study are to estimate the density threshold value to determine the influence of the sensor type, to implement features, to evaluate the degree of agreement of different annotators for training, and to determine the influence of architectural typology annotating a specific dataset for training. From an operational point of view, a dataset on which conduct the experimentation was selected. In particular, our scientific collaboration on the analysis of the architectural heritage of the Franciscan orders in Campania allowed us to develop a specific dataset on the typology of the Franciscan order. And a census of Franciscan architecture distinguished by province was carried out. At this stage of the research, we selected the Salerno-Lucania province. And in this province, the first case studies were identified to evaluate the answer to the research questions previously described, of which both terrestrial laser scanner and photogrammetric data were acquired. Now I leave the insights to my colleague Giuseppe Antuono.
Thank you, Valeria. The starting point of our work was to reflect on cluster recognition. employing the RF algorithm already trained by the FKPK unit. The annotation outcomes of our dataset were evaluated. The results show a partial recognition of the macro elements of the cloister typology, with the greater problems noted for the classes, moldings, and windows and doors. One possible cause is that the algorithm is pre-trained on a preliminarily annotated dataset without harmonizing the results of different specialization. So we worked on refining the data on which to perform the training. Firstly, we made a point cloud dataset more coherent with the architectural type of interest. The dataset consists of clouds manually annotated for the two case studies by operators with different specialization, age, and experience. Next, we evaluated the degree of their agreement by computing a final cloud with appropriate classes for the training phase. To evaluate this cloud, data were first normalized using a Python script, returning the clouds to the same number of points so as to eliminate any errors due to cleaning operations. The normalized clouds were compared, computing the final clouds as the result of calculating the trend of the classes assigned to each individual point, and the trend values made it possible to estimate the annotator's degree of agreement or disagreement. For example, the REAACH class showed the highest degree of disagreement among the annotators at 70%. This process is currently underway for the other case studies in the dataset. This will allow the algorithm to be retrained and evaluate the actual improvement in class recognition. Further considerations were made about the quality of the starting dataset. To evaluate the influence of density variation in the elements recognition, a portion of the initial points cloud was subsampled with a decreasing step. The subsampled clouds were classified to estimate the total number of label points compared to the total points number. A significant percentage of recognized classes is shown even by subsampling the 4 by 4 centimeter space cloud. On the other hand, for 8 by 8 centimeter step subsampling, the percentage of recognized classes decreases significantly. This reduction is because as the cloud density is reduced, so the number of points in the surrounding is smaller, returning as null feature values. This allows to deduce a threshold value of the cloud density step equal to 4 by 4. Above this threshold, value class recognition is not optimal, thus orienting feature digital survey action. Another consideration is to evaluate the sensor type dependence of classification outcomes. The information contained in laser and photogrammetric data are not the same. Consider, for example, reflectance, and could affect the computation of features. That said, to evaluate the sensor type dependence, we started by comparing the outcomes obtained from laser and photogrammetric data when the density of the point cloud changes. With the reference of the photogrammetric cloud, the segmentation obtained is inaccurate. Columns and wall was labeled in the same class. Moreover, it is visible that in the photogrammetric data, good results are obtained even with a step cloud density reduction of 4 by 4 centimeter. Nevertheless, the results are not comparable to those obtainable on a laser scanner basis. In addition, the percentage of recognition classes differs depending on the type of sensor, lowering significantly in the case of the photogrammetric cloud, probably also related to the acquisition methods. Considering that the class recognition is closely related to feature extraction and selection, further consideration must be given to the possibility of computing other features and the influence of their selection on the results. Our first action was to implement RF with additional features, such as linearity and anisotropy, The implementation was conducted in Python by also integrating the computation of the above features, so as not to use an external calculator. Once the number of features has been expanded, the question is how to choose them to optimize the elements recognition. Therefore, bearing the radii of the surrounding, different identification results were calculated for the geometric features on the left and the radiometric features on the right. The result on the geometric features computation show that it is complex to identify an ambiguous value of the radius, such as to return an optimal data classification, while the specific radiometric feature calculations show good identification of some classes, such as windows and doors. So we began to reason about which features are best for the recognition of each class. We can observe the first results in this table. For example, for the class REAACH, optimization can be performed using the features linearity, sphericity, anisotropy, and surface variation. The best selection will improve the training to return a coherent and functional classification to the architectural typology. I leave the conclusion to Professor Pierpaolo D'Agostino.
Giuseppe, only a few words in conclusion to highlight about the results and questions about how to manage and use point clouds to achieve good outcomes in terms of feature recognizing AI work. So I like that several issues are still open. Issues that need to be solved, such as to deepen which features are able to optimize a best recognition, depending also of detail achievable. Feature detail achievable to try to increase a subcategorization of features, and last but not least, to better understand how survey data, survey methodologies, and sensors could affect outcomes in AI categorization. In our opinion, in conclusion, this could be good investigation trajectories to definitely and probably currently consider AI application in cultural heritage domain as a mainstream, a useful mainstream application. And that's all. Thanks for your attention.